enhancement MOSFET, classic small signal transistor, transconductance model. Here already we have seen, ID also we have seen. ID current, these two conditions, VDS less than VD set, VDS greater than VDS set, VTH equal to, this is the equation, VTH naught plus gamma of root of mod 2 by f minus VBS minus root of mod 2 by f. Unlock circuits biased through current sources. Unlock circuits biased through current sources. OP as a function of drain current. OP as a function of drain current. Okay. Bulk enhancement MOSFET, classic small signal transconductance model. Here we here already I have seen, we have seen this one, small signal increments only, linear equivalent circuit, non-linear operating point. Here in this GDS, GM we have seen, GM approximately we have seen. In this GDS, this condition also we have seen. In GDS, okay, beta of VGS minus VTH. VGS, that is this voltage, okay, that is VGS, okay, minus thermal voltage. Actually VGS only, but up to VTH no function. That's why we are going to reducing that VTH from VGS. That is subtract. Where for what condition? VDS, this one, okay, this one. Okay. Less than or equal to VD saturation. Okay. Here, while VDS is more than VD sat, then VGS, then VTH, VGS deducting from subtract from VTH, subtract from VGS, then squaring. Here full beta value you are taking, but here half beta value only taking. Then here squaring, here not squaring. Multiply with here lambda, then equal to lambda ID equal to lambda ID. VDS greater than or equal to VD saturation. Bulk enhancement MOSFET model, same classic small signal transconductance model. Here asymmetrical parameters and non-explicit expressions. Symmetrical opposite asymmetrical parameters and non-explicit expressions. Here GMP equal to mu GM, mu GM, mu equal to gamma, mu equal to gamma actually divided by 2 pi f minus VBS. We have to mod of, because for positive value we have to the VPS value VBS to be deduct from 2 pi f, that is mod how much we are getting positive value only. If negative value coming only, we have to consider positive, then scaling by root, then multiply with 2 times. Here reducing, then multiplying 2 times. That's all. So mu equal to so GMP equal to MGM. No, sorry, mu GM. Okay. So this is the answer. Then here GMG, GMP, this one. Okay, this one. Here GMG, this is the GMG. Okay, GMG equal to dou ID divided by dou VGB. Okay, GMG equal to dou ID, dou ID here where this is ID, partially different is okay, with respect to dou VGB where in between here. Okay, VGB gate, in between gate and the base voltage, that is the GMG. Okay, sorry. Then actually what we are doing for dou ID only. Okay, then for VGB, where is that? This one, VGB. Okay, then VDB all are 0. Which one? VGB, okay. This one, VDB, ESP. This one 0 only. Okay, here in GMD, in GMD equal to dou ID. Okay, dou ID. Okay, with respect to VDB. Actually this G this is D. Okay, so VDB in between the train to base. Okay, so VDB equal to ID, then ID VDB. Where is their VDB? This one 0. Okay, so no. Here VGP is here 0, and then VSP 0 here. Okay, then see here direction. This one coming here, this one going up, this one down. Okay, then GMS we will see here. GMS, that is, where is that GMS? This one. Okay, GMS equal to, say, partially differentiate dou ID with respect to what? S for source. Okay, so VSP, that is source and base. Okay, it means ID, this ID, and then 1 minute. Here we got to negative. I also count to be count. Here 1 minute. Here negative value. Here no negative. Okay. Here no negative. Positive. Here only negative. Okay. Here, so here negatively coming. So here negative. Okay. ID, VSP. In this condition, VGB, VDB, VGB 0, then equal to, what will happen? NG. Okay, then here VGB already we have seen gate base CMG VGB for this GMS VSP for this, that's why going here for GMD VDP. Okay, then VSP in between this one VSP VDB VSP. Okay, then here, so we already have seen this one. Here source VDB not, but VGB is different. So VGB not when we have a VDB not with the adding with the VGB